And when you get iPhone 17 Pro on Spectrum, you get the same seamless connection you love at home. On the go.
The game Wordle has gone pretty viral in the last month or two, and never one to overlook an opportunity for a math lesson. It occurs to me that this game makes for a very good central example in a lesson about information theory, and in particular a topic known as entropy. You see, like a lot of people, I got kind of sucked into the puzzle, and like a lot of programmers, I also got sucked into trying to write an algorithm, some of them that would play the game as optimally as it could. And what I thought I'd do here is just talk through with you some of my process in that and explain some of the math that went into it, since the whole algorithm centers on this idea of entropy. First things first, in case you haven't heard of it, what is Wordle? And to kill two birds with one stone here while we go through the rules of the game, let me also preview where we're going with it. My first thought in approaching this was to take a look at the relative frequencies of different letters in the English language, how close your guess is to the truth. And to kill two birds with one stone here while we go through the rules of the game, let me also preview where we're going with this, which is to develop a little algorithm that will basically play the game for us. So I haven't done today's Wordle, this is February 4th, and we'll see how the bot does. The goal of Wordle is to guess a mystery 5-letter word, and you're given 6 different chances to guess. For example, my Wordle bot suggests that I start with the guess crane. Each time that you make a guess, you get some information about how close your guess is to the true answer. Here the gray box is telling me there's no C in the actual answer. The yellow box is telling me there is an R, but it's not in that position. The green box is telling me that the secret word does have an A and it's in the 3rd position. And then there's no N and there's no E. So let me just go in and tell the Wordle bot that information. We started with crane, we got gray, yellow, green, gray, gray. Don't worry about all the data that it's showing right now. I'll explain that in due time. But its top suggestion for our second pick, and there's crane, we got gray, yellow, green, gray, gray.
Oh, wow.
Don't worry about all the data that it's showing right now. I'll explain that in due time. But its top suggestion for our second pick is shtick. And your guess does have to be an actual 5-letter word, but as you'll see, it's pretty liberal with what it will actually let you guess. In this case, we try shtick. And all right, things are looking pretty good. We hit the S and the H, so we know the first 3 letters. We know that there's an R. And so it's going to be like SHA something R or SHAR something. And it looks like the Wordle bot knows that it's down to just 2 possibilities, either shard or sharp. And it's kind of a toss-up between them at this point, so I guess probably just because it's alphabetical, it goes with shard, which, hooray, is the actual answer. So we got it in 3. If you're wondering if that's any good, the way I heard one person phrase it is that with Wordle, 4 is par and 3 is birdie, which I think is a pretty apt analogy. You have to be consistently on your game to be getting 4, but it's certainly not crazy. But when you get it in 3, it just feels great. So if you're down for it, what I'd like to do here is just talk through my thought process from the beginning for how I approach the Wordle bot. And like I said, really it's an excuse for an information theory lesson. The main goal is to explain what is information and what is entropy. My first thought in approaching this was to take a look at the relative frequencies of different letters in the English language. So I thought, okay, is there an opening guess or an opening pair of guesses that hits a lot of these most frequent letters? And one that I was pretty fond of was doing other followed by nails. The thought is that if you hit a letter, you get a green or a yellow, that always feels good. It feels like you're getting information. But in these cases, even if you don't hit and you always get grays, that's still giving you a lot of information, since it's pretty rare to find a word that doesn't have any of these letters. But even still, that doesn't feel super systematic, because, for example, it does nothing to consider the order of the letters. Why type nails when I could type snail? Is it better to have that S at the end? I'm not really sure. Now, a friend of mine said that he liked to open with the word weary, which kind of surprised me because it has some uncommon letters in there, like the W and the Y. But who knows, maybe that is a better opener. Is there some kind of quantitative score that we can give to judge the quality of a potential guess? Now, to set up for the way that we're going to rank possible guesses, let's go back and add a little clarity to how exactly the game is set up. So there's a list of words that it will allow you to enter that are considered valid guesses that's just about 13,000 words long. But when you look at it, there's a lot of really uncommon things like ahead or ollie and arg, the kind of words that bring about family arguments in a game of Scrabble. But the vibe of the game is that the answer is always going to be a decently common word. And in fact, there's another list of around 2,300 words that are the possible answers. And this is a human curated list. I think specifically by the game creator's girlfriend, which is kind of fun. But what I would like to do, our challenge for this project, is to see if we can write a program solving Wordle that doesn't incorporate previous knowledge about this list. For one thing, there's plenty of pretty common 5-letter words that you won't find in that list. So it would be better to write a program that's a little more resilient and would play Wordle against anyone, not just what happens to be the official website. And also, the reason that we know what this list of possible answers is because it's visible in the source code. But the way that it's visible in the source code is in the specific order in which answers come up from day to day. So you could always just look up what tomorrow's answer will be. So clearly there's some sense in which using the list is cheating. And what makes for a more interesting puzzle and a richer information theory lesson is to instead use some more universal data, like relative word frequencies in general, to capture this intuition of having a preference for more common words. So, of these 13,000 possibilities, how should we choose the opening guess? For example, if my friend proposes weary, how should we analyze its quality? Well, the reason he said he likes that unlikely W is that he likes the long shot nature of just how good it feels if you do hit that W. For example, if the first pattern revealed was something like this, then it turns out there are only 58 words in this giant lexicon that match that pattern. So that's a huge reduction from 13,000. But the flip side of that, of course, is that it's very uncommon to get a pattern like this. Specifically, if each word was equally likely to be the answer, the probability of hitting this pattern would be 58 divided by around 13,000. Of course, they're not equally likely to be answers. Most of these are very obscure and even questionable words. But at least for our first pass at all of this, let's assume that they're all equally likely and then refine that a bit later. The point is, the pattern with a lot of information is, by its very nature, unlikely to occur. In fact, what it means to be informative is that it's unlikely. Much a pattern like this. Specifically, if each one that match that pattern. So that's a huge reduction from 13,000. But the flip side of that, of course, is that it's very uncommon to get a pattern like this. Specifically, if each word...
It's almost like getting a lot of information. Like getting a lot of information kind of like is equal to kind of like a big kind of like reduction of like, so, say you've got like all these words which are like possible, and then you reduce it to like, this small kind of amount. This is like, this process is lots of information. Kind of like the ratio between, I don't know, maybe you have like before and you have after, and it's like the ratio of B to A or something. Yeah, like if A is very, very small and B is like whatever, then if A is smaller than B, then this is going to be a bigger number. If A is much smaller than B, then it's going to be a much bigger number. So that could be kind of like measure of like how much information we just got from a guess.
Equally likely to be the answer, the probability of hitting this pattern would be 58 divided by around 13,000. Of course, they're not equally likely to be answers. Most of these are very obscure and even questionable to be the answer. The reduction from 13,000. But the flip side of that, of course, is that it's very uncommon to get a pattern like this. Specifically, if each word was equally likely to be the answer, the probability of hitting this pattern would be 58 divided by around 13,000.
The probability of hitting this pattern would be it's kind of weird. I can kind of see how that could be the case, but I don't know. I mean, I do kind of see the probability of 58 over this. The probability of this. I guess it's much more likely to get like the highest probability thing. Yeah, I don't know.
Of course, they're not equally likely to be answers. Most of these are very obscure and even questionable words. But at least for our first pass at all of this, let's assume that they're all equally likely and then refine that a bit later. The point is, the pattern with a lot of information is, by its very nature, unlikely to occur.
I mean, okay, I guess using like an extreme example, the pattern with a lot of information is unlikely to occur. So I say kind of like the most unlikely thing is that we just guess like the exact right word. So the pattern of kind of like green, 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 green. This is kind of like the most unlikely thing to occur. This match. So the probability of this is just equal to 1 over 12,972 to get like everything right. I think the issue that I'm having though is like mapping from this space, like this this kind of like guess space, tile space, green, yellow, gray space to the space of words here. Because if we kind of think about the total like number of possibilities here, I guess like in each square, it could either be green or yellow, green or yellow or gray. And so there's 3 times 3 times 3 times 3 times 3 times 3, which is equal to 3 to the 5th, which is equal to, so 3 cubed is 27 times 9. Well, 27 times 10 minus 1 is equal to 270 minus 27 equal to 270 minus 30 minus 3. So it's equal to 240 plus 3 is equal to 243. And 243 looks familiar, but all right. So there's 243 possible kind of guesses here, but yeah, these things aren't all equally likely. Like getting green, 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 green. Yeah, you kind of have, let's see, 243. So you basically you've got this space over here of the different kind of like guess things. So you got 243 of these. And then you've got words over here. It's like a much kind of bigger space of words. And so you got like W1, W2. Well, like let's do, for example, let's just do like, yeah, like waltz. But even better, it's like watch. And you've got like wuxia. So for example, so if you have the kind of, is it the case that more things are going to kind of like map to this one here, you know, from this space over here, versus, you know, maybe there's only like two things with this one? There's going to be more of these sequences which correspond to this word. I'm not sure about that.
In fact, what it means to be informative is that it's unlikely. A much more probable pattern to see with this opening would be something like this, where, of course, there's not a W in it. Maybe there's an E, and maybe there's no A, there's no R, there's no Y. In this case, there are 1,400 possible matches. So if all were equally likely, it works out to be a probability of about 11% that this is the pattern you would see.
If all the words were equally likely, this is the
most likely out. Of course, there's not a W in it. Maybe there's an E, and maybe there's no A, there's no R, there's no Y. In this case, there are 1,400 possible matches. So if all were equally likely, it works out to be a probability of about 11% that this is the pattern you would see. So the most likely outcomes are also the least.
This is the pattern that you would see.
Informative. To get a more global view here,
It's going to take me a while to figure out.
Show you the full distribution of probabilities across all of the different patterns that you might see. So each bar that you're looking at corresponds to a possible pattern of colors that could be revealed, of which there are 3 to the 5th possibilities.
Yeah, I think I'm going to pause it here. Probably a good place to stop. See you later. Peace.